In this video, we're going to review the equation for a straight line because we're going to be using it throughout the semester. And the way we're doing that is by deriving the relationship between Celsius and Fahrenheit. These relationships come from somewhere. Someone decided at some point that they were going to measure temperature different ways. The Fahrenheit scale, for example, set the coldest possible temperature as 0 Fahrenheit, which was an ice water ammonium chloride solution, and the hottest temperature in a particular seaside town during summer at 100 Fahrenheit. We normally use the Celsius scale in science, but the Fahrenheit scale on a day-to-day basis. And so we need a way to relate them. They're both what we call relative temperature scales, meaning 0 Fahrenheit is defined relative to something, ice water ammonium chloride. 0 Celsius is defined relative to the freezing point of water. And for that reason, they can have negative temperatures. So keep that in mind. Fahrenheit and Celsius negative. The Kelvin scale is what we call an absolute scale. That doesn't have a negative temperature allowed because it's not relative to some specific thing. It's kind of an absolute instead. Okay, so back to the problem at hand, the Fahrenheit and Celsius scale. The reason I'm going to derive this for you, other than to teach you how to draw a straight line, is it can be helpful for science to kind of understand where things come from. And that's what we call first principles learning. The title of the YouTube channel is First Principles Chemistry, because when I was a grad student at Caltech, we always learn things from first principles, which is not to say that you don't have to kind of have some general understanding of science. It's that instead of memorizing a bunch of equations and using the equations based on what you memorized, you kind of keep in mind the key guiding principles and then use those principles to derive any equation you might need. Now, obviously, since you guys are general chemistry students, I'm not going to expect you to derive equations, but I'm going to teach in that fashion, meaning it's always important for you to understand where something comes from and why it works, not just how to use it. Okay, that's the first step, is learning how to use something, learning how to write an equation, learning how to express something as a straight line or linear relationship. The next step is to understand when it works, when it doesn't work, and how to kind of circumvent issues where it might not work. So let's take a look at the data we're given. We are told that the 0 degrees Celsius temperature is the freezing point of water, and that's a reference point. And corresponding in Fahrenheit is 32. Most of us in California don't experience this 32 Fahrenheit, but if you ever lived anywhere else, you might have gone below freezing, which is below 32. At that temperature, you'll start to see snow and hail and sleet. Above 32, you can sometimes see something resembling it, but it's usually going to be rain instead. So it's freezing, that's a good temperature. These two temperatures correspond to each other. Less common probably is the temperature corresponding to 100 degrees Celsius, which is 212 Fahrenheit. It's unlikely you've experienced 212 Fahrenheit, although you probably have used stoves where the temperature goes above 300, 400, 500 Fahrenheit, depending on what you're trying to cook. So 212 is the boiling point of water. We want to create a linear relationship from this data. So what you should remember about lines is that straight lines go through points. Specifically, you need 2 points to create a straight line. So I'm going to list this as one data point, and I'm going to list this as another data point. And I purposefully chose the Celsius temperature to be my independent variable, x. And I'm allowing the Fahrenheit temperature to be my dependent variable, y. If you did this opposite, if you made x the Fahrenheit and y the Celsius, you'd still get a linear relationship. It's not just going to look the same way that we currently have. It's a rearrangement of what we have. I'm going to draw it graphically so you guys can follow along how we find the equation of the line. So on the independent axis, I'm going to put the temperature in Celsius. That's the x-axis. On the dependent axis, I'm going to put the temperature in Fahrenheit. And to find the equation of the straight line, I need to know 2 of the data points. So those 2 data points are listed here. So we could call this one, for example, x1, y1. So when the temperature is 0 on the Celsius scale, it's 32 in the Fahrenheit scale. That's the first data point. That's at 32 degrees Fahrenheit. And when the temperature rises to 100 degrees Celsius, then that's going to correspond to 212 Fahrenheit. Okay, these are our data points. To find the equation of the straight line, we need to know how to find the equation of a line. And you guys should all have experience finding the equation of a line from your algebra classes. I'm going to cheat and use a ruler or a straight edge. You guys can just hand draw this. That's fine too, unless you have a ruler on you. So it looks actually like a straight line. And that equation is derived algebraically one of two ways. Probably the one you guys are more familiar with is the equation y equals mx plus b. And that's the one we're going to end up using here. It's more convenient. But you should know that there's other ways to write the equation of a line, and we're going to use them later in the semester. So y minus y1 is equal to m minus x1. This equation is called the point slope equation, and this one is called the slope intercept. And the reason why we have different ways to write them is it's going to be based on what information we currently have. What do we already know about our data? Specifically, if we know the slope of the line and the intercept, this equation is easiest to use. If instead we know a data point and a slope, this equation is easier to use. Generally, we're not going to know the intercept, so we're going to use this one more often, but this one works okay here. So you should know what the slope is. So in these equations, m is going to represent the slope. x1 and y1 are data points, and it actually doesn't matter which data point you pick. You could pick the y2 and the x2 or the x1 and the y1, just telling you pick a data point and know the slope. And b is the intercept. The intercept is the point when x is equal to 0. So specifically, it's the y-intercept. When you put in x equals 0 here, this term goes away. Y equals b. What's the value of y when x is 0? That's what the intercept is. You should remember from algebra that slope is defined as the rise over the run. So specifically, the slope of a line measures how much the y value changes. So this is what we call delta y, over how much the x value changes, which we call delta x. The rise is how far it goes in the vertical direction over how far it goes in the horizontal direction. So y2 minus y1, this is the value of y2. This is the value of y1. That's how different this is in height. And divide that by x2, that's this value of x, minus x1. That's how far it increases going horizontally. We have all the data points, so we can find the slope of this line, and that's how you would determine the relationship between Fahrenheit and Celsius, assuming you want it to be linear. So let's put in those numbers. Notice they match up with my labels here. One data point is 100 and 212. They match each other. The other is 0 and 32. By knowing two data points, we can find the slope, specifically 212 minus 32, y2 minus y1, over x2 minus x1, 100 minus 0. We find the slope of the line is 1.8. And I want to point out something here because it's going to be important for you to remember that that's actually an exact number. It turns out to be exact because 0 Celsius is an exact measurement. It's exactly defined as the freezing point of water. 100 is exactly the boiling point. And the Fahrenheit scale has been redefined so that 32 is exactly the freezing point of water and 212 is exactly the boiling point of water. It's similar to what the original proposed Fahrenheit scale is, but not the same. Since every number is exact, this one's exact. I could put infinite sig figs, but I'm not going to, it's just extra work. To find the equation of the line, we need to know the slope. And just to remind you, my temperature in Fahrenheit is my y, my temperature in Celsius is my x. We know the slope, and we need to know what the y-intercept is, which is b. That's sometimes challenging to find, but in this case, you should be able to answer it. If you don't remember what a y-intercept is, make sure that you review the sections at the back of the book with algebra. So take a minute to think of that. You should have gotten for the value of b that it's 32. And here's why. When I plug in x is equal to 0, this goes away, y has a value of 32. We have the y-intercept right here. When x is 0, what is y? It's 32. So that gives us the equation for the conversion between Celsius and Fahrenheit. I just put back in the actual symbols for Fahrenheit temperature and Celsius temperature. We multiply the Celsius temperature by 1.8 and add 32 to get the Fahrenheit. If you had done the reverse, let's say, for example, you had taken the Celsius temperature and put it on the dependent axis and you would put the Fahrenheit temperature on the independent axis, you would have gotten the equation Fahrenheit temperature minus 32 divided by 1.8. And sometimes you guys might also see this 1.8 written as 9/5 or in the reverse written as 5/9. All those numbers are exact, so keep in mind, this 32 is also exact for the same reason that I said before. That's why we can write this as a fraction. It's an exact number. So it'd be 5/9 Fahrenheit temperature minus 32. It's the same relationship, just written in reverse. Now, what if we had used the point slope formula? It turns out you would get the same answer. And in fact, it's helpful for you to remember how to write it. So you put in first the slope, which we just found, and then you pick a data point. So start with this one, because that's the one we used before. It'll give you the same equation, but make sure that you understand whether you use x1, y1 or x2, y2, you get the exact same equation because they go through the same data point. Either way, you get the equation of the line. This linear relationship comes from 4 numbers. 3 of those numbers are easy to remember. 0, 100, we use those all the time in chemistry. 32, which those of you who haven't lived in a climate where it freezes, probably not as common to you. The one that's the least common is 212. As your instructor, whenever I need this relationship, in my mind, I do this math. You might think, why would someone do that? Why would you be insane and do something like that? It turns out because doing this in my mind is much more efficient and actually adds meaning than memorizing this equation. It's not wrong to memorize it. At the level you guys are at, memorizing is fine because you're learning things. So that's why there's still memorize this, learn that. You don't really understand the depth of everything yet. But as you get further and further along in science, what you find is understanding where something comes from is way more important than the result itself. And so being able to derive things like this will start to become more and more common as you get to higher levels. You'll see in the homework that having this ability allows you to solve problems that are not like this at all. It's a skill that's learned.